All right, here comes the day 3 video, and this video is about 8.5 and 8.6 from Algebra 2 Trig, and this is actually the end of the Algebra 2 Trig part of this unit. After this, we'll be going into the pre-calc part. Warm-ups, as you know, I'm always going to do those, not in video, but as part of class time. Okay, what is conditional probability? We actually have already talked about this a little bit. Conditional probability is this whole given that idea, so we're just going to be diving into that a little bit more now. So it's it's the B given A. We were doing that when we were doing things like marbles out of a bag. And once you've changed a kind of future probability, you've changed a second stage kind of probability, you have to account for that. Like once we know A has already happened, how does that change the probability of B? So what's the new probability of B given that A has already happened? That's kind of what this first paragraph is talking about. Okay, so they're revisiting the warm-up. Okay, do I need to go back and do the warm-up for this then? Given that a student takes biology, they're explaining it here, so maybe it'll be okay. Given the student takes biology, what's the probability that he also takes economics? Okay, so we're given that a student takes biology. So this is now the new kind of sample space. This is kind of now the new denominator. So we're looking out of the biology students. Out of the biology students, how many take economics? Okay, it turns out, I'm going to have to do the Venn diagram. I can't figure this out. All right, no problem. We'll just do the Venn diagram. We'll just do the, I have to erase all this kind of separately. All right, different than my notability. Okay, so let's make the Venn diagram for this. This is fine. 50 students. So we have 50 in the sample space. We have biology. That's 35. We have 25. That's econ. And we have 5 for neither. So what's the total? Let's finish the Venn diagram first. So if I added up the 35 and the 25 and the 5, that would be too much, right? That would be 65. That's way too much. How much too much is it? Well, it's 15 too much because we're talking about 65 and it's supposed to be 50. So that's how much I've overcounted, so the 15 has to go in the middle. And if you fill out the rest of the Venn diagram, you realize that, yes, that would work. 20 plus 15 plus 10 plus 5, that does that to 50. Great, life is good. So you pick a student at random, so that's going to be out of 50. How many don't take biology? As long as we're here, let's just do this whole thing. How many don't take biology? Well, that's everybody but the 35. How many take B and E? Well, I figured that out last. That was the 15 in the center. Or, well, we already knew there were 5 that don't take either, so there's 45 in the whole snowman. Are taking biology and economics mutually exclusive? Oh, this is great. Oh, yeah, these are great questions. This is no, not mutually exclusive because this intersection is not empty. There are, actually, maybe this would be better. There are 5, oh, that's weird. There are 15 who actually take both. 15 take both. That intersection is not empty. You don't have to, you're not excluded from taking, oh really? Come on. You're not excluded from taking economics if you take biology. Are they independent? Okay, this is a lot harder. Let's try to see, and I talked about this a little bit recently. I can't remember if it was in the second video or in the first class, but we're trying to see, here's the test, here's one of the tests for independence. Does it work out that this is true? If you can multiply and you get the same thing as if you just said and, the probability for and, then you know they're independent. But I'm going to figure these out kind of separately and just see if they're equal, see if we can kind of prove this. The A and B I know is 15 out of 50. Ugh, I can't make a nice 5. 15 out of 50. Is that the same as, actually I shouldn't say A and B, should I? I should say, let's make this a little more relevant to the situation. This is bio and English. Bio times probability of English. Probability of bio is 35 out of 50. Probability of, not English, economics. Economics is 25 out of 50. These are not the same. The probability, these two right here, this little thing is going to equal something like 17.5 out of 50. That's not the same. So no, that means no, they're not independent. There are, and as long as I'm here, let's kind of talk about this. 15 out of 25 people in economics are taking both. 15 out of 35 in bio are taking both. That's, maybe that's not a good way to explain it. Let me say it this way. 15 out of the 25 people who are taking econ, that means if you're at the econ party, 15 of the 25 people are in bio. If you're at just, the school, we know that inside econ, overall, out of the whole 50, there's 35 out of everybody takes bio. These two things are not the same. This is technically like the probability you're taking bio given that you take econ. This is the probability you're taking bio, kind of overall. Those aren't the same. So the given that econ, which we have talked about, like we've talked about recently, like the let's figure out the probability that you're taking bio given that you're taking econ, which is good because that's what this whole worksheet's about. If we factor in the econ and then say, okay, now it's a probability you're taking bio, that's different, right? That's a different probability than just taking bio. So the taking econ does affect it. The probability you're taking bio is affected by the probability you're taking econ, because I know that because I know these two probabilities are different. Let's do that like 6 more different ways, shall we? Okay, so given that the student takes bio, what's the probability that they take econ? Okay, so out of all the bio, that's where I got the 35, but I had to make this Venn diagram so I could see what the numerator is supposed to be. The numerator would be, well, the people who are in econ within this framework, or within this kind of new sample space of the bio. Among the bio people, what's the probability you're taking econ? That's 15 out of 35. So that's 15 out of 35. Which, yeah, we can reduce. That's 3 out of 7. Probability of B given E. Then that's going to be out of the econ circle. And the econ circle is this circle. Out of that circle, out of that 25, how many people are taking bio? What's the probability of bio given econ? That's 15 out of 25. So it's the same numerator, but it's out of a different denominator. Now it's just out of the econ people, which is 3 out of 5, and these are not the same. This is not a test for independence. The fact that those two are not equal, that's not about independence. That's just about find this and find this. That's all we just kind of did there. Okay, 50 students went on the Thrill Seekers holiday. 40 students went whitewater rafting. 20. Yeah, this is the same kind of problem. So, I'm kind of thinking we can save this one for class. This is exactly the same as the one we just did. All right, this one's a table, so this one's going to be different. In order to determine the relationship between these things, all right, I'm just going to draw these here right there, because I think that's going to be helpful to separate the totals out from everything else. Is probability that got less than 6 hours of sleep and passed the exam. This is just an and. So here I'm just looking at an intersection of the two kind of rows and columns, or a row and a column intersection out of the 120. So got less than 6 hours of sleep is this top row, and pass the exam is the first column. So this is just 12. Got less than 6 hours of sleep or failed the exam. So again, it's out of 120. But now this is like got less than 6 hours of sleep or here. So how many people are in those, like in one or the other of those two things? It's like everybody except the 90. So I know that's like these 3 all together, these add up to 30. Yeah, or you can just add those up. Let's get all this out of the way. But yeah, this is going to be 30 people out of the 120, which is a quarter. Pass the exam given that, okay, this is new. So now the new denominator, if you haven't figured this out yet, that's the denominator. That's my new sample space. Given that that they got less than 6 hours of sleep. So out of 6 hours of sleep, that's just these people. So we're just looking in there now. So out of those 22 people, how many passed the exam? Again, we're just looking in the top row. That's 12. Another given that. So now we're just looking at the pass the exam people. That's 102. Out of those 102, so out of this group, how many got more than 6 hours of sleep? That's 90. Oh, can I reduce that? Does this reduce any more? Oh, it might. Oh, yuck. One more time. We'll divide by 3. I think that's right. All right. Are passing the exam and getting more than 6 hours of sleep independent events? Okay. Couple ways to do this. I think so far the one we've learned the most is does the and equal the multiply? So let's do that. And a lot of times, especially in AP Stats, if they ask you this independent question, sometimes you can look back at the previous question. Like that always comes at the end or very late in the problem. And they've asked you some stuff before this that you can kind of use. Let's use part A because there's an and at least in part A. So probability of less than 6 and pass, is that really the same as probability of less than 6 times probability of pass? There's that other test that I think is a little bit more contextually makes more sense, but we'll use this one for now. There's the 2 different tests for independence. You know what? You know what? Oh, let's do this. I'll make a little highlight box. Right here I'm going to say other test. We'll do this in class. The probability of A given B doesn't equal probability of A. We'll do that one in class. Okay. Yeah. And then, so we're back to this one. Right. Probability of less than 6 and pass. We figured that already. That's 1 out of 10 from part A. Does that actually equal probability of less than 6? Okay, probability of less than 6 is 22 out of 120. Probability of pass is 102 out of 120. Okay, now I need a calculator. Okay, and I get, this is 1/10, and this is, some huge fraction, but it comes out to be something like 0.155, which is not equal to 1/10, so not independent. That's all we're going to say for now. Those aren't equal, so they're not independent. Okay, in a survey of the number of science courses being taken, we've got, this is a 3-set Venn. I think it's a 3-set Venn. I think I'm going to set up 3-set Venn, because setting up a 3-set Venn is kind of hard. I think I did it in a recent video, but this is something I want to see over and over again. I'm going to set up the 3-set Venn, and then I'm going to leave the this for class. Okay, so let's do this. Chemistry, physics, bio. Chemistry is 21. You think 3-set Venns are hard? What do you see? A 4 or 5-set Venn? All right. Physics is 24, and bio is 17. There's a lot of bio stuff today. This one looks like the most important piece of information right now. I'm going to put this 2 in here first and say, let's take care of that. I've kind of taken care of those. 5 students take physics and chemistry. That counts the 2, because those 2 people would say yes. If you ask them, do you take physics and chemistry? They would say yes. So they are counted in the 5 here. Physics and chemistry, 5. 4 take chemistry and bio. Chemistry and bio, 4 total. And 3 take bio and physics. That's 3 total. Okay, now I can fill out the rest. 21 minus the stuff, I'm looking at chemistry. 21 minus the stuff that's already accounted for is 21 minus 7. Physics is 24 minus 6. And bio is 17 minus 5. Okay, but I'm going to stop there for now, because there's a lot going on with these. Given that sets, I think that would be great for class time, but setting it up, you might want to see that over and over again. Okay, and that's it for lesson 8.5. 8.6, can we do this warm up in class? I'd really like to. Oh yeah, we could definitely do that in class. Why is it jumping around like that? Cards, yeah, that's a good class time stuff. Okay, so we talked about one of these tests. Oh yeah, that's the test I've been using over and over again. The other fact here is that, oh, this is wrong. Oh, let's fix that. This is the definition of the probability of B given. Oh, you know what? Sorry, no, this is right. This is about if they're independent. Yeah, if they're independent, this is true. They're independent, this is true. This also, I'm just going to add to it then. This is the probability of B given A. And so I was about to tell you, the other test for independence is if this is equal to this, then it means they're independent. This is true all the time. Sorry, this is true all the time. So, yeah, if the probability of B given A is the same as probability of B, I think we talked about this, in a previous video or in person, that it's by adding the given A into that equation, if the given A doesn't change the probability of B, that's like the best way to say that the probabilities are independent. Given A doesn't matter. Given A doesn't affect B. That's what independent kind of means. So yeah, the way that's printed, there's nothing wrong with that. I'm just kind of adding to it, saying here's another test for independence. But the thing I'm just putting there in parentheses is true all the time. It's true whether or not they're independent. So if they are equal, then this is the new kind of thing. And yes, they would be independent. That's the other test for independence. But in dependent events, and that's what they've kind of written here, this is true all the time. Actually, you know what I kind of want to say? I'll say it this way. These are true in general. It's just if things were independent, they would be kind of silly, but they would still be true. It's not like they have to be dependent for you to use the rules on the right side here. Because if independent, that would actually equal the probability of B. Now it just looks like this. And if they were independent, this would just equal the probability of B, and that would look the same. So I kind of want to say general on this side. And independent is special kind of on the left. Anyway, it's not wrong. I'm just trying to be kind of more explanatory. Recall that when we compute the probability of an event given that, we're computing conditional probability. Yeah, okay, great. Said that. Example 1. Do we need... Why do I keep doing that? Yeah, you could... I think it's a good idea to do this as a Venn diagram. And it's not in counts, notice. It's in percentages. M is 0.55. I think it's still good to do Venns. B is 0.18. And the both here in the middle is 0.05. So we can figure out what the rest of this stuff is supposed to be. That's 0.50. We can figure out what the outside is supposed to be. Actually, do we need the outside? 55 plus 13 is 68, I think. Yeah, so the rest is 32, like if you needed to do that. The question is, are they independent? Oh, sorry. Determine probability of M given B. M given B, then, is the probability of B on the bottom, which is the 0.18. Out of that 0.18, so again, now we're focusing our attention on this 0.18. Out of that, how much is also M? You could look back at the formula where, the formula it said this is the probability of both out of just the probability of B, which I guess they gave me everything I needed there. I didn't really need the Venn. This is just 5 out of 18. I think the Venn helps. I actually do think the Venn helps. Okay. This is the conditional probability with the tree diagram. Great reason to use a tree diagram. Okay. You get forbidden items in the luggage. Sometimes the alarm goes correctly. Most of the time it goes correctly. Sometimes there's a false positive. Sometimes there's a false negative. I think I kind of talked about this in class when I talked about medical examples on the AP stats. Problems that do that all the time. Okay, so there's whether or not the bag actually has the forbidden items in it. And then from that kind of tells us what the probability is that the alarm's going to sound or not. So that's the driver kind of, is whether or not there's something in there, something forbidden in there. And then we'll know whether or not the alarm's going to go off, probabilities based on that. Okay, so 5% have it. That's where this goes. 95% don't. If it has a forbidden item, so now given that there's forbidden, so we're on the top branch here, there's a 98% chance it's going to say beep, beep, yes, and 2% chance it wouldn't. If it doesn't contain the forbidden stuff, there's still an 8% chance it's going to go off, but 92% of the time it will correctly say no. So find the probability that a random bag contains a forbidden item and triggers the alarm. So that's right here. The probability of F yes is 0.05 times 0.98. So how many of the bags are going to be sort of correctly identified? That's this. I guess I should write this down here. Probability of Fy equals 0.05 times 0.98, which is 0.049. Find the probability that the randomly selected bag triggers the alarm. Okay, well that's also good to include these. It's going to be F yes or no yes. I guess not forbidden and yes does trigger the alarm. So it's also going to contain this set, which is the 0.076. No yes. So this is 0.049 plus 0.076. Notice there's more in the second category. That's interesting. 0.125. Given that it triggers the alarm. Given that it was yes alarm. Maybe I should use A. I don't know. I'm calling these yes. Sorry. Given that it did trigger the alarm, what's the probability it actually has the forbidden item? So this is out of what we just, and this is the way, I kind of asked this as a bonus question on day one, I think. And this is the way they always do it in AP Stats. Given the probability we just found, right? That's this is all the cases that trigger the alarm. What's the probability? And that was, remember, adding up both of these. It was adding that one and that one. Out of those two cases, what's the probability it just has to be this one? Or, it's that one out of both of them. So, whoops, 0.049. 0.049. So just that one out of all of the yeses is something like, this is like, remember it was the one about the there's one about the coaching and the goalie and the soccer thing. It's like, given that we just know what the outcome of the second one was, which means it had to come from one of these two, what's the probability it was the top one out of the possibility of both? You might want to, maybe it makes more sense to write that this way, to write it all out. That's where we got that. Okay. You can look at that if you need to. 6-sided die, and then we get a ticket. We can have these different tickets. make a sample space. What's the probability of, okay, this is kind of interesting. I think I do want to do, well, why is that? Sometimes when I have the pen, it uses the pen, and sometimes when I want to just scroll up, it thinks I want to draw. I don't. Okay, so we're going to do one of these. We're not going to do both. Let's do the first one because I think it looks a little more complicated. Let's do that one together. Why is it twisting? All right. Okay, so we need a die, and the die is either going to turn out A or B. What's the probability of A? What's the probability of B? It's 5/6 A and 1/6 B. And then to figure out which jar we're picking out of. In jar A, it's 2 pink and 5 green. So that's 2 out of 7 and 5 out of 7. And in B, it's 4 pink. That's a pink. That's a green. It's 4 pink and 3 green. Those are still out of 7s. This was a 5. Okay, so represent the sample space. That represents the sample space. I'm not going to draw the ends of it yet till I need to. Find the probability the ticket is pink and it was drawn from jar B. So probability of jar B and then pink. That's going to be this one right here, which is 1/6 times 4/7, which is 4/42 or 2/21. Okay. Determine probably the ticket was pink, so we have to add these together. So this is 2 out of 21. Actually, you know what? I'm going to keep my common denominators. This is 4 out of 42. This was 10 out of 42. So we'll say 10 out of 42 plus 4 out of 42, which is 14 out of 42, which is miraculously exactly 1/3. Calculate probability the ticket would chosen would be given that. Okay, there's a given that. So the pink goes on the bottom, and guess what? We just determined pink. So this 1/3 goes on the bottom. The probability that goes on top is pink and jar B, which is what we had to compute in the first question. So let me write this out. Probability of B given pink is the probability of B and pink divided by the probability of pink, which is what we have here. So let me multiply fractions like this. That's 6 out of 21, which is divided by 3, 2 out of 7. Okay, and like I said, we'll do the other one in class. It's almost the same kind of thing. We'll do it together. I'll talk you through it. Sample space. And again, oh, come on. Let me use my finger to scroll up and down. Is this kind of the same thing? Should we do this together? Do I need to make this video any longer? I'll start the tree. And then we'll do this together from there. So, all right, we have one spinner, then the second. Actually, I might just do the whole thing. So you have a spinner that goes, there's 3 possibilities. It's red, green, blue. And those seem to be pretty equal. And then, the other one's also equal. Oh my gosh, you know what? Maybe, maybe a tree isn't the best way to do this. I'm gonna have 4. There's 12 on each thing. It says create a model to represent samples. I could also make a table. Oh wait, there's 2 reds on here. Never mind, this is gonna be easier than I think. Let's just make these 3 each. And each one of these is gonna be RGB. RGB. I got smaller, that went down. And the thing is about the reds are all half. And the other thing about this tree that's kind of silly is that, that's a half, is that this second stage branching, 1/4, 1/4, 1/4. I wish you could zoom in on your test paper as you're writing it. These 3 stages of this second part of this tree diagram, they're all the same within them, so that seems kind of like a waste of space. This might have been better as a table. As a table, it would have been more like, like the 2 dice, where we could have done, let's just talk about this. We could have done the table like spinner 1, spinner 2 kind of thing, and the first one could have been red, green, or blue, and the second one could have been, I guess it was 4 things, or 3 things again, 2, wasn't it? Actually, no, it should be 4. I had that right the first time. This is going to be like red, green, or blue. So this would be red, this would be red, this would be red, green, this is red, blue. These are going to start with green, red, green, blue. This might be quicker to do it this way. Yeah, there's nothing wrong with that either. First spinner is red and second spinner is blue. How many of those are there? Yeah, we could look at either the table or the tree diagram. Yeah, since I have both here, then the compare and contrast kind of thing, that might be kind of interesting. Um, yeah, first spinner red, second spinner blue. It looks like there's only one way to do that in the tree. Red, blue has to go that way. And so that's a third times a quarter. That looks like it's 1/12. Or in the table, first red, second blue is got to be that one. That's the only one that goes red, blue. So either way, it looks like it's 1 out of 12. What's nice about the table is everything in this table is equally likely. That's 1 out of 12. These 9 choices here are not equally likely, and we would know that by multiplying through the tree. Okay, determine P probability the first spinner is not red, and the second spinner is not blue. Okay, I'm going to count these up here. First spinner is not red, and the second spinner is not blue. Not red and not blue. So that's not red and not blue, 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 not red and not blue. I think it's those 6. Yeah. In the tree, it would have to be those 2 branches, and then the second after that, the second one can't be blue. So those 2 and those 2. I'd have to count those up. I'd have to multiply all that stuff. It looks like it's 1, 2, 3, 4, 5, 6 in that one too. Also, okay. All right, so I'm gonna get rid of all blue. Get rid of all this stuff as we go on. Anyway, this is gonna be. I counted up 6 out of the 12, which is a half. I counted probably the first spinner is red, or the second spinner is blue. I like the table better. I don't know if you do by now, but I kind of do. First one's red, which would include all of these, or the second one's blue, which would include all of those. It's kind of like the dice the first day having a 6 at all. I see 7 of them there. 7. Ooh, I don't want to highlight that. 7 out of 12. And first spinner green, given that the second spinner is blue. So given that the second spinner is blue, we're only talking about those. Out of those, so that's now my sample space. So out of those 3 possibilities, what's the probability that the first spinner is green? It's 1 of them. Yeah. Okay, I think that's it for this worksheet. I will see you in class.